Okay, so, last year I was visiting Manuel in Sydney, and we were sitting together and trying to narrow down onto our common interests, and after some iterations we came up with this list here. We were both interested in domain-specific embedded languages. We both had some interest in dependent types. We had both done previous work on generative programming. Don't worry about the D, it's just to make everything start with D. And then Manuel has this generative Manuel has this long-standing experience with data parallelism, about which I didn't know anything, so that sounded like an interesting thing to get into as well. So our plan then was to construct a language or a front end that kind of deals with all these things at the same time. So the mission that we set ourselves was to construct a dependently typed generative data parallel programming language. Big mouth. And how would we want to do that? Because of previous experience, we thought that Agda might be a good platform for doing that. And so the plan was to build an Agda front end for the Accelerate language. And Accelerate is something that Manuel has been doing in previous work. And I'm going to tell you a little bit about these substrates now to start with. Okay, so what is Accelerate? So Accelerate is a data parallel array language. That means the prevalent data type is arrays, and the essential operations that you can do on them are the usual bulk operations that you all know, like you can fold arrays, you can map over arrays, you can scan arrays, I mean all these kind of things. And it supports, of course, multi-dimensional arrays in a very nice way. And it also has an extremely expressive embedding into Haskell, which uses, I wouldn't say all the loops in Haskell's type system, but it pushes it quite hard. Another thing that it does, it's a generative language, so the code that you write isn't just executed right now, but instead the code that you write really is translated into abstract syntax, and then at some point it generates GPU code from that. Well, actually there are several backends for that, but so one of them just interprets the term, and then there are at least two backends that generate code for different styles of GPU bindings. And if you're interested in more about that, then there's a paper in 2011 by Manuel and his collaborators. And just to get you some example here, there's code for the dot product, which takes two vectors of floating point numbers and computes the dot product. So what's notable here? Will I get this to disappear? No.
Click somewhere outside that panel.
And don't move anywhere. Yeah. Okay, right. So what do you see here? So here, the incoming things, x's and y's, these are, you can imagine them to be standard Haskell vectors, which is not quite true. Then this use thing converts them into something, references that are usable inside of the abstract syntax. And then this last line here, actually, it looks like some operations, but really it just generates abstract syntax. And you see it here in the type. So here these add things are really just abstract syntax for operations. And later on, in the second step that you'll see in the next slide, there's going to be a run function that actually translates this, stretches this onto the GPU and executes it. You'll notice that here we have the plus and 0 and star operations. And here we are exploiting, or Accelerate exploits Haskell's nice overloading facilities to overload all these symbols to actually generate code instead of executing something. So essentially there's a higher order abstract syntax specification behind it. Let's not go deeper into that right now. To actually run it, you need one of the implementations of a run function that I already mentioned. So one is one particular backend is the CUDA backend that uses the CUDA library to generate code, and then you pass this and one of those act things, and it just returns the value of it. Yeah? And what happens behind the scenes is, at one time of your Haskell program, it grabs this code that you generated, compiles it to GPU kernels, loads the used arguments, so you remember the used x's and y's on the last slide, loads them along with the code onto the GPU, executes, and then transfers the whole result, which might be a huge array, in this case it's just a number, retrieves it, and then your Haskell program can continue with that. Yeah? Works really, really great. So, just to give you a glimpse of what kind of typing is already involved in Accelerate, so the vector and scalar types that you saw in the previous slides, they're just instantiations of a general array type. So scalar is really an array of dim 0, and the vector is an array of dimension 1, and these are again shorthands for a type level, for a heterogeneous list notation to denote dimensions. So essentially below it there are two data types. One is Z, which stands for the empty dimension, and then there is another data type with this constructor, unpronounceable constructor, that just allows you to stash on another dimension. So the trick behind this is, of course, that if you use this kind of data structure, then this structure is replicated on the type level, and that's what Accelerate uses in order to make sure that the dimensions match up in the right ways in the operations. Right, Agda has been introduced already nicely by the previous two speakers, so I don't need to say too much about it. It's a dependent functional programming language. The main feature that we are going to use here is that there are inductive data type families and that there is dependent pattern matching. And at some point we also thought we might make use of dependent records or parameterized modules. But you'll see, and then there are lots of additional facilities there. And it's also an interactive proof assistant, but this is something that we really unfortunately didn't need to make much use of in this work. So the standard example, just to get you into the mood of the main application that we've been able to exploit here, is that you have a vector type that's indexed by its size. So I don't really think I need to go through that slowly, because this is really the standard example. Yeah, so the empty vector is indexed with 0, and then the non-empty one is indexed with 1 more than its rest. And what it boils down to then is that then you can use this kind of types to enable safe accesses where no runtime bounds checking is necessary anymore. Yeah, so this get operation here is built in such a way that you have to provide it with a proof that the index is in range for the array, and then you can, by construction, you're certain that at runtime no bounds checks can happen. And there are several ways of encoding it, and this is one which uses an explicit proof that the index you're looking at is less than the size of the array, and this is inductively defined data. So there are different ways of encoding this, and this is one way that you might use here. Okay, so then we thought about various ways various places where we could make use of dependent types in Accelerate. And these were our expectations. So one, which is why I had this other example on the previous slide, is of course we wanted to augment the array shapes with static size information, because that's the main thing that was missing from the shape information that's already present in Accelerate. So it knows everything about the number of dimensions, but it knows nothing about the different sizes. Second thing that we wanted is, for example, for float-like operations, you need more than you would like to have more information about the operations that you pass than just the dimension information, and I'll talk about that in a minute. And then, of course, we don't want to lose any of the Haskell examples. Yeah? So there's already some code basis that is being developed with the existing accelerate, and of course, if you construct a stronger front end, you don't want to lose any of these examples, right? So you don't want to lose expressivity. Unfortunately, not all of that really works out, and so one thing that works nicely is the bounce checking, so that works out really well, with some maybe surprises, we'll see. Then the correctness guarantees for code line operations that we were after didn't work out at all, but maybe some of you has a good reason why this can't work, or a workaround to suggest here. And then we found out that using the straightforward encodings, we couldn't even express all the Haskell examples. And if time permits, I'll also show you some of that. So let's first, to get into the Agda part, let's first transcribe the dot product example in Agda. And as you see here, it looks quite familiar, right? So here these three vector data types, they correspond to just vectors, and then the kind of underdoors data types, they correspond to the generated abstract syntax. And apart from that, apart from syntactic differences and some workarounds, because, well, Agda doesn't have this nice way of overloading constants, right? That's a bit worrisome. Apart from that, you can write this example quite nicely. Yeah, so this prevector is a real vector of n elements of type float, and then the scalar is a reference to a piece of code that evaluates to such a scalar. Yes.
What is the zero triple column float?
This is a string.
Yeah.
So this is the way that we embed constants. So this is a string, and this is a parsing function that's indexed by the type at which you want to parse it. So Agda doesn't know numbers, right? Yeah, so it has some way of parsing natural number literals into its internal representation.
Yeah.
But here we actually would like to have float constants.
Okay.
Also, the float that you hear is not a type really. So there's more detail about that in the paper. I don't really want to go into that here. Yeah, so it looks natural, but some of the looks are deceiving. All right. So the array type. Of course, below that there is the array type. The array type is indexed over a shape. Well, but now the shapes contain size information in just the way that you would probably expect. So in Agda now you can define the shape like this. Well, first of all, you can collect the shape construction into one data type, which isn't done in the previous encoding in the existing encoding. And the second one is that now you can have a constructor for the shape which actually includes the net, the size of the dimension. Yeah, and then vector and scalar are just like in the Haskell version, they are just specializations of the shape indexed array type. So it looks pretty much the same here. So but here the difference is the vector is indexed by the length, and here in the shape you put the actual length, whereas in the accelerate version you would just say z:int at that point.
So your shape is just
it's essentially a list of integers, a list of naturals. Yes. Okay, now, as I said, bounce checking works well. So in dot product, you saw the zip width function, and now if I write this code here in Agda, and I have two arguments here, array of shape and A and array of shape and B, then Agda makes sure that not just the number of dimensions matches up, but that also the particular sizes of the dimensions match up. So the arrays have to have the exact same shape. On the one hand, this might be that we want. On the other hand, it's more restrictive than what Accelerate actually implements. So what Accelerate actually implements is it's taking the minimum everywhere. Yeah? So if you remember the way that Haskell's list function works. If one list is shorter, then your result will just be the minimum length of the two lists. And that's what Accelerate also does. Well, this is a nice and crisp type in Agda. You can, of course, also encode the other behavior in Agda, but then you have to do the calculation on the type level as well. Well, in the indexes as well. Yeah, you can do it, and this is code that you can use to that. Well, so you need some auxiliary stuff. You need to make sure then by hand that the shapes match up, for which you need one way of doing it is to specify it via such a relation here, and then if the shapes are equal, then this function here can be defined that just computes the minimum overall dimensions. Yeah, but if you want to have all the examples from Haskell and to be able to transfer this, then you probably need to get into this extra problem. And similarly, if you look at fold and fold 1, then here you can also do bounce checking in fold and fold 1. There's so that's the definition here. There's not really much to do. The only thing that you want is fold works for any array which has at least one dimension. For fold 1, a non-empty array is required. And that's something that you can very easily express. In Accelerate, the types here are essentially the same. So here this is the type of the argument array. It just says, okay, I need at least one dimension, and this last dimension is folded away. And for fold 1, the type looks essentially the same. So it just says, I have an array with at least one dimension, and this gets folded away. Of course, in the Agda version, you can express that by just putting the successor. So that works. Okay, so why am I mentioning? So that's not very spectacular. Why I'm mentioning fold and fold 1 is because there's another issue with it, which is connected with the second part. So as you may remember from the definition 2 slides back, fold and fold 1, they both partition their argument in some a priori unknown way in order to parallelize it efficiently and get to log n runtime for the operation. And if you want deterministic results of these operations, then the operation must be associative, and maybe sometimes you also want to enforce that, in case of fold, that the E is also a unit with respect to the operation. Well, that's all well known. You can express such stuff in Agda. So great. Let's just change the signature of fold and ask for a monoid to be passed in. And then we fold over this and the elements of a monoid, and then we can make sure that we get deterministic results. Sounds good. And you can, of course, encode monoids in Agda. So this is one way, or you can use the much more sophisticated encoding that's in the standard library. After you've found it, which may take you a day or maybe 2, or 10 messages. No, but one message to the mailing list will suffice. But there's a catch, unfortunately. And the catch is one thing that you already observed. So one thing, the E in the signature of fold, it's not a set, but it's an element of a data type that we have defined in Agda in order to encode the Haskell type statement. So it's not a set. But it's just an element of the data type. The other one, the bigger catch, is that the type of the operation here, well, let me go back here. This one here, it's not E to E to E, but it's expression of E to expression of E to expression of E. So this is a function that handles abstract syntax. Associativity of syntax is quite meaningless. So, I mean, we looked at some ways of how we could put things together there and finding some syntactic arguments to do associativity, but we didn't really get something useful there. And even if you say, this is the abstract syntax for a class, what's the meaning of class here? So even then, if you wanted to prove over this syntactic stuff, you needed to formalize an interpreter and that knows something of the semantics. So that seems quite unfeasible to prove associativity at this level. Too bad. Right. So there's another limitation, which due to time limitations I won't be able to get into. So it has to do with the filter operation. There's a section about it in the paper, so it cannot be easily implemented in Agda. And there's a nice workaround with it. So there's more information about this filtering stuff in the paper. So furthermore, there's some more information about the representation of types and constants. So what you've seen here, the float thing, of course, Agda doesn't have a float, so we have to come up with some way of representing that. There are some further examples there. And there's a whole section dedicated to the description of the implementation, which is using the foreign function interface of the Alonso compiler. And this is really messy. So because the original accelerator already has a rich type structure, and the foreign function interface is not very expressive, you need to kind of forget some information and encode it and reconstruct it back on the Haskell side. So it's a bit involved, but it's all described in the paper. Right, conclusion. So our initial expectations were only partially met. Bounds checking works well, but other things like the associativity and didn't work out well. Also, we hit on some limitations like this filtering that I wasn't able to show you right now. Nowadays, some part of the bounds checking, I believe, could be done with the lifted data types that you have in the recent Haskell releases. It just wasn't available to us at that point. And another thing is, as you might have seen here with the, so you already got a glimpse of that with this associativity problem, but this filtering problem also shows it quite nicely. Sorry, you'll have to look in the paper. It looks like generative languages do not fit extremely well with dependent types. So in case of the filtering thing, the point is that you are, after filtering, the size of the resulting array is essentially unknown. And since you're generating code, you cannot even get some evidence for the size of the resulting array to wrap in an existential or something like that. So it's not there because you haven't executed the code yet, right? So we didn't see a way out of that. But any of you has good ideas? Okay, thank you. That's all.
Questions? Yes.
Sorry. Assuming you would solve the associativity problem in the way you approached it, wouldn't the real world associativity or floating point in silicon make an end to this anyways?
That's another question if you wanted to accept that, but then you wouldn't have then you couldn't do many of the optimizations that array libraries and so on do.
Yes, but then you have to accept that that there is something like in
that you introduce some kind of error.
Yes.
Yes, maybe, yeah, of course. Well, or you would have to strengthen your argument and saying, okay, the numbers that I'm dealing with are essentially in a similar size. Or with multiplication, it would be fine, right?
If you know your data in advance.
If you know enough of your data, but sometimes you know it, right?
My point was rather the other way around. If you don't have associativity in silicon in the end, why making so much effort to prove it in the first place?
Okay. Well, I mean, but for multiplication, it's there, right?
Well,
For addition, you don't have associativity.
Not sure you have it for multiplication, do you? Not sure you have it for multiplication. For real machine floats, it's not precisely associative, is it?
Not? I don't know.
no.
No, it's associative either. Okay, good.
Yeah.
They're slightly fuzzy. One last quick question before we finish. Yeah,
Is zip width being the minimum of 2 arguments, is that a feature, in Haskell or a bug? I mean,
You could argue either way, right?
because if you could, many of, semantics of APL, which is dynamical type, is heavily actually, complicated by the fact that you have to have all these kinds of cases when things don't match. And actually they make the reasoning harder, and they make actually the implementation also a lot harder. So in particular in a data parallel implementation, we'd like to avoid all these boundary conditions because they give you a branch divergence in the code if you don't watch out. And if you had a guarantee that says like, I happen to have actually, vectors that really fit together, then the code would be a lot easier. So, I mean, a lot easier to generate very efficient code.
I think it's a good point for if you deal with arrays, that you really want the zip width function that insists on shapes being equal. For lists, I've seen sufficient number of applications where, for example, one argument of zip width is an infinite list, and the other argument is a finite list, and you exploit exactly this feature in order to get a simple specification.
But you're not going to try and upload the infinite list to your GPU and run it there, right?
No, of course not. I mean, for arrays and in this context, I guess that you actually want the shapes to match up exactly.
Okay, we should stop there and thank people.